Tigadan 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 pam pam tigadan 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 pam pam tigadan 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 pam pam tigadan.
Up next from Ghent University is computer science Kenneth Hoste. He's going to be speaking from EasyBuild to Easy. Kenneth, how are you today?
I'm doing great. Thank you very much for the invitation.
Absolutely.
Set up the screen share. That should be popping up.
Looks great on my end.
All right. And I'm good to start.
Yes, you are.
Okay. Thank you very much. Once again, thank you everyone for inviting me. I'm happy to be part of this. I also wish it could be in Lugano. I've been there before several times. It's a very nice city. If you ever get the chance, definitely take it. So I'll just very quickly introduce myself. I'm indeed a computer scientist. I got my degrees at Ghent University in Belgium. And right after completing my PhD, I also joined the HPC team there. So I've been there for, over 20 years. Wow. My main tasks here in the team are focused on user support, and a big part of that is installing scientific software. And as a part of that role, I inherited the maintenance of EasyBuild, which is the tool I'll be talking about in the first part of the talk. And I also became the lead developer and eventually also release manager of EasyBuild. There's a whole bunch of things I like, including free and open source software. There's also things I don't like, and most of those are related to the work I do on EasyBuild. So I've been swearing on some of these tools for a long time. So EasyBuild, for the people that don't know it, is a tool, or we often say a framework for getting scientific software installed. Whenever we can, we prefer to do that from source. So we compile the software from source. The reason we do that is because we have a strong focus on Linux and HPC systems, supercomputers, where performance is a very important aspect, as was clear also from the previous talk and the follow-up discussion. So we pay a lot of attention to try and make sure we get the most out of the hardware by properly installing the software, properly compiling it, building it, using the right compiler options, and so on. EasyBuild is implemented in Python. We have support for running both on top of Python 2.7 and a recent Python 3. It integrates with the environment modules tool that is often or almost always there on HPC systems. And we support different variants of that, environment modules or LMOD. EasyBuild is open source software. You can download it through GitHub or through the Python package index, so that the standard location where you can download Python software. It has support for a range of different tool chains, different compilers, different MPI libraries, different class libraries, and so on. And in total, we have over 2,600 different software packages. So without different package versions or without extensions, so things like Python packages, R libraries are not included in this count, supported today. So that's a big pile of software. EasyBuild was originally created by the HPC Ghent team in Belgium, but now it's supported and developed by a worldwide community. So from a very high level, how does EasyBuild work? Well, you have the EB in the main command. You give it, you somehow tell it what to install. In this case, we're giving it the name of what's called an easy config file, a build recipe for TensorFlow, a specific version of TensorFlow that should be installed with a specific compiler toolchain. That's the FOSS 2021A part, and a specific version of CUDA. So when you hit enter, EasyBuild will start doing that installation. There's lots of stuff going on in the background here. It will download sources for you, unpack those sources, set up a build environment, do the compilation, so the build phase, and then the installation, and so on. And eventually it will complete. It will create an environment module for you, and then you can load that module and start using that software. Specifically for TensorFlow, there's a lot of magic going on in the background here, and it actually took us quite a long time to get this fully working the way we want it to. So building TensorFlow from source is not trivial. But thanks to EasyBuild, it's now very easy. You can basically do it with the push of a button. So how did we get to this point? EasyBuild started well over 10 years ago. Originally, it was an in-house project at the HPC Ghent team. It was started in the summer of 2009 by Stijn de Weert, who's the tech lead at the HPC Ghent team. Over time, we developed it internally. It was redesigned a couple of times with the help of summer interns. We originally didn't have a test suite, so we figured that was a good idea to make sure that the code or the tool keeps stable, or stays stable, keeps working the way we want it to. After a couple of those iterations, we were happy enough with it to release it to the world and see if it could be useful for other people as well. We couldn't find any tool like this when we started EasyBuild, and it looks like we were one of the first that really were ambitious enough to try and organize all these software installations for HPC systems. The first stable version of EasyBuild was released at Supercomputing 2012, and from then it really took off and a community emerged around it. It took us a while to have proper documentation, so we did have a wiki, but that was a bit of a mess initially, and with some help from a consultant, we set up some proper documentation, which was a big help to the community, of course. We also started doing community meetings or hackathons, so we actually had 11 of those shortly after the public release of EasyBuild, and that in those hackathons we were helping people to enhance EasyBuild the way they liked it, or implement features, add support for more software, things like this. We did this all over Europe, including at CSCS at some point, and also at TAC in the US. Next to that, we also started getting scientific software installed sessions at both EESSI and ISC to get the word out about EasyBuild, but also to look around in the community which other tools were there that could be interesting in that same area. Then time progressed and we started doing backwards incompatible changes based on the feedback that we got from the people that used EasyBuild. CSCS was actually quite an early adopter of EasyBuild back in 2015, especially when we looked into the integration with the great programming environment. Another major version where we switched to LMOD as a default modules tool, and we had stable integration for GitHub, and I'll talk a little bit more about that later in the talk. We also switched from hackathons to actual user meetings, which were more about presentations about how are people leveraging EasyBuild on their site, or tools related to EasyBuild that could maybe be combined with it, and so on. EasyBuild 4.0, where we added compatibility for Python 3, and we got rid of all Python dependencies because that was becoming a pain and people were running into trouble installing EasyBuild because of that, so we got rid of those. And more recently, we also started doing tutorials at ISC. That took us a while to get a tutorial proposal accepted, but now it looks like once you get in once, it's easier to get in again because people know it will be a good session. And last but not least, we were also selected as the main installation tool for the Lumi pre-exascale system in Finland. So the high-level feature summary of EasyBuild, I think most people know more or less what EasyBuild does. So it allows you to fully autonomously or automatically build and install scientific software, no matter how nasty the installation procedure is. It generates module files for you. It logs thoroughly what it does archiving so you can reproduce builds later. You can configure it. Pretty much every aspect of it can be configured in different ways. And it's actively developed and there's frequent stable releases. Some specific features as well that you can dynamically extend it so you don't just have EasyBuild itself, but if you're writing a bit of Python code on the side, you can make it more capable in various ways, or you can customize it. We're very serious about testing things, so whenever we support something, we make very sure that it keeps working. And it really has grown out to be a worldwide collaboration across HPC sites across the world. Some recent enhancements as well for people who have been using EasyBuild for a while and have maybe not been keeping up with all the updates we've been doing. Some of these I'll go into a bit deeper in the coming slides. Like, for example, the site customization that you can do through hooks. So you can customize the behavior of EasyBuild by writing fairly simple Python functions and just giving them to EasyBuild and asking, please pick these up whenever that makes sense. And the example in the slide shows the pre-configuration hook that you can implement to change one of the OpenMPI configure options. So the with verbs, if you want to replace that with without verbs in case you don't have any InfiniBand network, for example. This is one way to do it. So this is a central way with a small bit of Python code, and that way you don't have to change all the build recipes wherever with verbs is being used. You're basically doing it on the fly as EasyBuild sees it popping up. So that's just a pre-configure hook. There's pre and post configure hooks, pre and post hooks for every installation step. There's a start hook. Whenever EasyBuild starts, it will trigger that hook first, and then you can already take any action or manipulate some internal data structures if you want to, and so on. So some EasyBuild sites are using this quite extensively. There was a talk at the last EasyBuild user meeting on how the University of Brussels is using this to configure their MPI installations on their heterogeneous cluster, which is a bit of a challenge, but thanks to EasyBuild hooks, it has a quite easy and clean solution on how they do that. And of course, this is well documented in the EasyBuild documentation. Then a bit more recent, we also started looking at what we call EasyStack files. So EasyStack files are a description essentially of the software stack that you want to install with EasyBuild, written in YAML. Has been supported for several EasyBuild versions already, but it's still an experimental feature because we're not fully happy with the feature as it is right now. And we know there are some enhancements that we want to implement. And because of that, we want to keep the freedom of essentially breaking how this feature currently works before we make it fully stable. And there's an example on the right that shows the description of a small software stack that includes GrowMax built with 2 different tool chains, 2 versions of OpenFOAM and a version of R. And that gives you an idea of how you can describe the full software stack that you want to manage with EasyBuild. Then another enhancement or change that we made recently is the adoption of FlexiBLAS in one of our main compiler toolchains, the FOSS common toolchain. So what we're doing here is rather than linking software directly with a BLAS library like OpenBLAS or Bliss or MKL, we're linking it with FlexiBLAS, which is a wrapper library essentially around all these actual BLAS or layback libraries. And that allows you to select the different BLAS or layback backend at runtime, essentially. So in the example, we're loading an application that is linking with FlexiBLAS, and rather than using the default OpenBLAS backend, we can tell FlexiBLAS to use Bliss instead. And we don't have to rebuild or relink the application at all. FlexiBLAS is making sure that in the background, it's actually using Bliss rather than OpenBLAS. So that gives you a lot of flexibility. You can play around with your application with different BLAS libraries. You can have a software stack where for some applications you use OpenBLAS, for others you use Bliss if there's a good reason to do that, and so on. The performance overhead of this wrapper is essentially, non-existent. So it's measured in clock cycles per function call, and usually BLAS and layback function calls take a good amount of time. So the overhead is basically negligible. It also gives you additional capabilities. You can enable profiling, and then when your application finishes, you get a small output file that tells you how much time was spent in which of the BLAS and layback functions. And this may be interesting for optimizing further the software. So we had an EasyBuild tech talk on FlexiBLAS by the main developer of this. So definitely take a look at that if you want to know more. And there's a related, or let's say a similar library for MPI, which is called MPI Trampoline, which would give us pretty much the same capability. So we would link applications with MPI Trampoline, which is again some kind of wrapper library, and that allows you to switch at runtime in the background to different MPI implementations like OpenMPI or MPitch, or even vendor MPIs like Cray, MPitch, and so on. So that if we would have both FlexiBLAS and MPI Trampoline in our toolchains, we get a lot of flexibility in terms of what we actually want to be using at runtime. And a small and mostly cosmetic enhancement to EasyBuild is that it can produce some rich output and progress bars while it's doing the installations. All you need to do for this is install the rich Python package. So if you do a pip3 install of both EasyBuild and rich, and then you start running EasyBuild, you will get these progress bars automatically. That's just a nice to have, and it gives you some information while the installation is still running, how things are progressing. Then one of the issues we had, or that we were not happy with, is the installation of R. So the R recipe, the R easy config we have, includes over 1,000 extensions, so 1,000 R libraries from the CRAN standard library online that we install along with R. So it's a batteries included installation. That was taking a very long time because each of these extensions were installed in sequence. So some of them have to be installed first because they are a dependency for other extensions. And EasyBuild was just chugging through these one by one. Even though it has several cores available to do the installation, it wasn't really using those cores yet. That is now changing. We have an experimental feature that tells EasyBuild to just install whatever extensions it can concurrently. So if there's 10 cores available, it will try to do 10 extension installations at the same time. And of course, it takes into account the dependencies between the extensions. That speeds up the installation of R quite a bit. So like a factor 3, 4, 5, if you have enough cores, is very easy to achieve with basically no effort. So you just configure EasyBuild to do the parallel extensions and install, and then it does it for you. This is still experimental because what's there works for R, but only for R. It doesn't work for Python or Perl or other types of extensions yet. And we want to fix that first before declaring it stable. And there's also some other issues like it doesn't know about R packages that are installed in a dependency. So that has to be fixed as well. But this is a feature that we hope to make stable for the next major version of EasyBuild, EasyBuild 5. And this will then become probably the default way of installing things that involve extensions. Then looking at the EasyBuild community, what we're seeing here over the years, the number of contributions we're getting is steadily growing. So last year we had close to 2,500 easy config pull requests per year. So that's not even talking about the other components of EasyBuild, EasyBlocks, and the core, the EasyBuild framework. And we're getting those from over 100 different contributors. So that's good, but it's also a challenge. So we need to keep up with these contributions. We need to talk to more people since we're getting more unique contributors per year. And this seems to be growing and it's not really slowing down. So yeah, that's something we'll have to keep up with. To some extent, this is also self-inflicted because we have this GitHub integration in EasyBuild, which essentially boils down to allowing you to make contributions straight from the EasyBuild command line. So EasyBuild has a new PR option, which tells EasyBuild to take an easy config file or an easy block or another part of EasyBuild that has changed and to make a pull request for that straight from the EasyBuild command line. So you don't need to even log into GitHub manually or click around in the web interface. It does everything for you. And that's, of course, that lowers the bar significantly to making contributions to EasyBuild. And that's also what is driving this growth in contributions. So yeah, we're getting more contributions. We're also getting contributions in a structured way. So it does help us as EasyBuild maintainers as well to keep on top of things. What we're also seeing is the number of supported software packages in EasyBuild has been growing over the years, pretty much at the same pace in the last 5 to 10 years. There's a small dip there because when we released EasyBuild 4, we got rid of some old stuff that is no longer actively being used, apparently. So software that's no longer relevant, let's say. So that was the small dip. We got rid of some things that are no longer supported. But from then on, it's been again increasing as it has been before. And last year we broke the limit of 2,500 different software packages, again without versions or without these extensions like iLibraries included. So that's a big and a very varied amount of software that we support. So this is not slowing down, and that's also a bit of a concern because the more we support, the more difficult it becomes to make sure that EasyBuild keeps working for everything that we have supported before. So this is definitely a challenge going forward. Then diving into the second part of the talk, and some of these things were already briefly mentioned in the previous talk as well. We see that the landscape of computational science in general is changing in different ways. So this explosion of available scientific software applications is one thing we see. Especially in bioinformatics, people use lots of different small tools, and it looks like, or it feels like sometimes these tools are popping up every other week. People are creating new tools or finding new tools that they want to play with for their scientific research. But this is becoming bigger and bigger, and that's a concern. We're also seeing more code being published than before, probably because there's some pressure on researchers to also publish their code, make it available, so other people can build on top of it, and so on. Also, the wider adoption of HPC resources, like, for example, the use of GPUs in bioinformatics, is also a part of this. So people realize that these GPUs are a very capable resource also for bioinformatics, so more software is produced to make good use of these resources. That's one aspect. Another one is definitely the increased interest in cloud, both commercial cloud and also on-premise cloud infrastructure, like they also have at CSCS. That makes things difficult. So if you go to the cloud, you can easily build your own cluster, but then how do you get the software that you need there? How do you make sure it's properly optimized for the hardware, the resources it will be used on, and so on. The growing variety in CPUs, so processor architectures or microarchitectures, so it's also a concern. So AMD is definitely back in the game. We're out of the, let's say, the era where Intel is king. This is definitely changing quite fast. Intel and AMD are still x86, so that's sort of okay, even though if you're paying close attention there, it's already a concern. But then we see ARM on the horizon, definitely with big systems like Fugaku or NVIDIA Grace that's coming up real soon. And in the longer term, we also see RISC-V, for example, through the European Processor Initiative project. So in the scope of Euro HPC, there's definitely a lot of attention or a lot of work being done on RISC-V CPU architectures as well. So where we are today is not the end, it's even going to get worse in the coming years. And that's then only CPUs. We see a similar trend for GPUs and accelerators. NVIDIA is getting competition from AMD already, soon probably also Intel. And then there's these special purpose accelerators like TPUs and IPUs, or things like this, which are definitely becoming relevant for many research domains as well. So that's all problems. And then the manpower in HPC support teams isn't really growing to be able to keep up with that and to support the scientists that want to use all these resources. So that's an issue. So we feel it's time to take the next step. So EasyBuild helps a lot with managing scientific software stacks today, but it's not enough anymore, and it certainly won't be enough in the future. HPCs are still losing way too much time in getting the scientific software that the researchers need in their hands, so getting it installed on the system, getting it properly installed on the system. That's still taking way too much time, and we can do a lot better. Especially for new software that's not supported in tools like EasyBuild or Spec. It's a big investment to get them supported there and getting them installed well. And often whenever people run into trouble with EasyBuild, so failing installations, it's usually due to small differences in their system configuration, in their setup. Sometimes trivial things like this partitioning, how big /temp is, for example, or how much memory they have in the system can have an effect on whether installations work or not. And this situation is actually getting worse. So there's more software, there's increasing variety in hardware. This is all not helping, of course. Next to this, we also see a lot of potential for more extensive collaboration. So we're already for 10 years now have been collaborating in the EasyBuild community on getting software installed. But there's steps after that which are very important as well, which we're not really collaborating on currently. A couple of those include ensuring that the installations are correct. So EasyBuild does what it can to check on itself and to make sure it doesn't produce anything that's utterly broken. But it's not actually checking the scientific results that are produced. That's the next step to make sure you're giving high quality installations to your researchers. And then keeping an eye on performance and making sure that performance doesn't regress is another important aspect. Reframe is definitely a good step in the right direction here, but there needs to be more collaboration, we feel, across HPC sites for this. So this is where the EASY project comes in. EASY stands for the European Environment for Scientific Software Installations, and that's gamed a little bit we can call it EASY, since there's a big tie to the EasyBuild community here. EASY is a collaborative project. It's, let's say, grassroots, so it was built out of need from HPC sites that want to enhance their collaboration together, since just using EasyBuild or collaborating on EasyBuild as a tool is not enough. What we want to do in the EASY project is build a shared central stack of optimized scientific software installations. So we want to have a central stack that can be used on any HPC system, but also in the cloud on workstations or laptops of researchers and so on. So it's a uniform way of giving properly optimized software installations in the hands of users, regardless of what system they use. So whether it's an HPC system or a Raspberry Pi, it should just work. And of course, here again, there's a strong focus on performance, also on automation. So making sure these installations are done automatically with as little human intervention as possible. Testing those installations, also keeping an eye on the performance of those installations and so on. So this is a high-level overview of the EASY project. It consists of multiple layers. The gray part is the host operating system. So your current Linux distribution, whether it's Red Hat or SUSE or Ubuntu, it doesn't really matter. We have 3 layers on top of that. The green part is the file system layer. That's how we distribute the software stack that we provide in the EASY project. And we do that with CVMFS, which is a file system essentially that works through HTTP. So it's like streaming installations whenever you access an installation and it's not available locally yet, it's actually downloaded in the background for you. And that's fully transparent to the end user. So this is how we distribute the installations we provide. Then we have a middle layer, which we call the compatibility layer, which levels the ground across the different Linux distributions. So we shield ourselves from the operating system, the host operating system, as much as possible to then build applications on top of. And that's essentially what containers are doing as well. So containers include a partial operating system as well to basically make the host operating system irrelevant. You can look at it as containers without the containing. So we have this middle layer just like containers do, but we're not enclosed in a container like you usually are. And then on top of this, we built our software layer. This is where the optimized application installations are and all their dependencies. And this is where we currently use EasyBuild and LMOD and a small Python library, Archspec, which can automatically detect what type of CPUs you're running on. So the long-term idea is to install this or to support this software stack on a large variety of hardware. We already do this for Intel and AMD and ARM CPUs. We have played around on power as well, but we don't see that as a very important target currently. And in the long term, we're also keeping our eyes on RISC-V, and we'll try to get that properly supported as soon as that's reasonably possible. We're heavily using or relying on Reframe for testing this software application, so the top layer, but also the compatibility layer, and making sure that it all works the way we want it to. And the way we make this all happen is by pulling together lots of open source projects like EasyBuild and Reframe, but also Ansible, Terraform, Singularity, or soon Aptainer to make this all happen. And yeah, as some people will probably know, this is heavily inspired by what Compute Canada is doing with their software stack. It's really pulling this open to more different CPU architectures for one, and also trying to make this a real community project where anyone who's interested can contribute to in one way or another. So this is a high-level overview of how the software distribution works. This is essentially just what CVMFS does. There's nothing unique here to the EASY project, but this gives you some sort of idea. So the software repository that we provide is provided by a central server, and then there's mirror servers around that basically distribute this all over the world. In the US, in Europe, typically have these servers sitting there to ensure fast access. And then whenever you want to use the software on an HPC cluster or in the cloud, you're basically pulling those software installations on demand from one of these mirror servers. And that's basically fully transparent. It looks and it feels like it's a local file system, but you don't really know that. So how does Easy work? How do you get started? It's essentially 3 steps. So the first part is to get access to the Easy repository. If you have admin privileges on your system, you can install CVMFS system-wide and install the Easy configuration file, and you're done. That's all you need to do to get access. Or if you don't have any admin rights, like for example on an HPC cluster, then you can use our small client container, which includes CVMFS itself in the container, and that's good enough to get access to Easy. And the second step is to setting up your environment. So you just source a script, which does some auto detection of what type of CPU architecture you're on, and then you're good to go. You can start loading modules for the software you want to use and start using that software. So it's very difficult to make this any easier than this. So Easy opens up a number of different use cases, like, it's a uniform software stack, as we already mentioned, but you can also leverage this in a CI environment, like GitHub Actions, for example. You can mount Easy in there, and suddenly you have this whole collection of software installations available to you that maybe provide dependencies for you or the newest compilers that you want to try and make sure your software works with, and so on. It also makes it very easy to set up infrastructure for HPC training. So whenever you need any scientific applications and they are included in the Easy software stack, you can just set up a throwaway cluster in a cloud environment or play around on your HPC cluster if Easy is available there for that HPC training. And then when the training participants go back home, let's say, they can easily get access to that exact same software environment by mounting Easy on their own resources as well. We also see this as a way of enhancing collaboration with software developers and application experts. We hope that we can work together with them to make them look at how we install their software and tell us whether we're doing a proper job or if we can or should change or improve things a bit. And we also see it as a way of relieving the developers from the burden of getting their software installed. So I can imagine lots of developers of scientific software get lots of questions on how to properly install it or problem reports that people are running into. And that's not really what they want to focus their time on. They want to focus on the science of the application and not to fix compiler errors, problems in the environment of the users. So the current status of the Easy project, this started shortly before the pandemic, which has been interesting because it wasn't exactly how we imagined to start a project like this, but yeah, it happened. So we've been mostly doing online meetings or exclusively online meetings since mid-2020. There's currently no dedicated funding for this, but that's something we're actively pursuing to get funding for this. But even then, we've been able to set up a proof of concept pilot repository, which has a couple of complex software installations, scientific software packages like Chromax, OpenFOAM, TensorFlow, all built from source and built for different targets that include Intel and AMD CPUs, ARM CPUs, more specifically the Graviton 2s that we have in AWS, and also some support for Powered 9, but that's far from complete. If people want to play with this, take a look at the Easy documentation and look for the pilot repository section. What's also interesting here is that we're getting a significant amount of sponsored credits by both AWS and Azure to help us with the development of this project, and we can easily play around in their cloud environments and do whatever we need to do to make this a successful project. And it's an active, ongoing effort. We're looking at lots of different aspects that we want to improve. If people want to get more information on the Easy project, I strongly recommend taking a look at the Easy paper that was accessed, that was published very, very recently, which is quite a long paper. It talks about the motivation for this project, what we want to do, what the design is like, what the challenges and limitations are, and all the different use cases that this enables. One thing we motivate the project with a bit is that we, something that's often overlooked. So the impact of building your scientific software like Chromax, for example, for a specific instruction set the impact of that can be quite big. So here we show in the green bar, if you're running GROMACS on an Intel Skylake system that supports AVX 512, you're getting good performance. If you're running binaries that are not optimized for that, then you're losing a lot of performance. And that's definitely something you need to keep a good eye on. Yeah, in the paper, we also show like a proof of concept, again, with GROMACS, that a GROMACS provided through EasyStack can perform really well, even if it's not specifically optimized for a system or using any system MPI libraries, for example. That doesn't mean you can't get good performance. You actually can. This is, of course, only one application, but it does confirm that this kind of concept can work well in practice. And also, some people in Microsoft Azure have experimented with this with Wharf, and they're seeing very similar things. So very good scaling with Wharf, even though they were just using Wharf as is in Easy without making any changes to it specifically to their type of resources. Yeah, that was it. There's a lot of links here to click if people are interested. And I hope there's time for maybe 1 or 2 questions.
Thank you, Kenneth. Yes, we do have one question from Joseph. He's asking, this is interesting, but isn't this functionality similar to NVIDIA NGC?
NVIDIA NGC, the containers, in some sense, maybe it is, but it's very different. So if I go back to the overview slide, so this kind of setup is way more dynamic than containers are. So the compatibility layer in some sense is different, but the software layer is something that evolves over time. As applications get added in the software layer, they automatically pop up on whatever system that Easy is being used on. So you don't have to update the Easy installation or anything. Whenever you have the Easy repository mounted on your system and applications get added in there, they just pop up all of a sudden, they're there, and you can start using them without making any effort. So with containers, you have to pull down the new container. You have to know that they are there before you can actually start using them. The containers can be very big as well, which is not really a problem here, because when you're accessing a software installation, only the files, the binaries that are needed for using that software are being pulled down fully transparently in the background. So you're not downloading gigabytes of files that you're not going to use. Only the bits and pieces that you actually need at runtime will be downloaded. So it's a very different concept from containers. It's way more dynamic and way more flexible.
Okay, thank you. Hussein, do you have any questions on your side?
Thanks, Brian. Thanks, Kenneth. It's very interesting, actually. Yes, you covered very well the problems and how you are just trying to sort out all these problems. Yes, I will also go back to the cloud part. And we already started a discussion with Sadaf earlier, talking about performance and how we handle that in a cray environment. And I think so far that would be also interesting to look at the cloud part, maybe on premises, not on the cloud provider, where we mentioned that earlier, where we have a case running Slurm under Kubernetes, and we can see that the Slurm components, I mean, here talking database, the controller, and the Slurm daemon, they are all running as containers there. And when a user log into a container, they will submit their jobs, and from there they can see the entire environment. They have compilers, they have the modules, they have everything there. And maybe it could be just an additional problem here. You can listen to your problems and see how that could be also customized, and how that could be helpful also to include in what you mentioned.
Yeah. One thing I can quickly do here, and I don't have a lot of time for this, but like I mentioned, one way to access Easy is through a container, actually. So we have a small, what we call client container, which is essentially hosted here on, well, it's hosted, this one is still hosted on Docker Hub, I think. But all this includes is a base operating system, in this case CentOS 7, and CERN VMFS. That's all that is in the container. So it's very, very minimal. It doesn't have TensorFlow or GROMACS or God knows what. But if you run this script, it essentially will drop you into the container. So this is cached, this should be quick. So once you're in the container, you have access to the Easy CVMFS repository. And in here, if you source our init script, and this is pretty smart and pretty cool, It actually auto detects what type of CPU you're on. So it notices this is an Intel Haswell, and then it will use that part of the software stack that's optimized for Intel Haswell. So it will make those modules available. And then using this, you can start checking, do I have GROMACS? Do I have TensorFlow? Do I have OpenFOAM? And you'll see all these modules available here that are served from our, in this case, pilot repository of Easy. So with a very, very minimal container, you can get access to a very rich set of software. Whatever we have in Easy will be available to you. So even if you're using containers for whatever reason in your private cloud infrastructure or God knows what, this is something that's really aligns with this as well. And of course, this is only one way of accessing the Easy software stack. What you typically do is have a native CVMFS installation, definitely on HPC cluster, and then you don't need any containers at all. It really integrates well with the entire environment.
Yeah, I'll be very happy to test the similar workload, because just that will make our life easier, definitely in this case, especially just dealing with such scenario. Yeah, interesting. Yeah, thank you. That's yes, definitely that's the first step. Let's say. I mean, we don't have the complement. We'll be working on this little by little, but that's the right approach. Thank you.
Okay, thanks a lot.
Thank you, Kenneth. Appreciate the presentation.
Tigadan, tigadan, pam, pam, tigadan, 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 pam, pam, tigadan, 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 pam, pam, tigadan.